In the dark corners of the cosmos, hidden from ordinary sight, lie vast clouds of gas and dust, cold, quiet, and ancient. These are molecular clouds, the birthplaces of stars. Within them, silence reigns, until gravity whispers. Slowly, gently, gravity begins to tug on denser regions of the cloud. These pockets collapse inward, growing hotter, denser, and more turbulent. What begins as chaos becomes the foundation of a new star. In places like the Orion Nebula, a stellar nursery just 1,344 light-years from Earth, we witness this cosmic alchemy. Here, young stars are born from collapsing gas, their fierce light carving through the darkness, illuminating the very wombs that shaped them. Each star begins as a protostar, a glowing embryo still feeding from the cloud around it. As it gathers mass, nuclear fusion ignites in its core and a new star is born. What we see in star nurseries is not just creation, it's transformation. From the dust of ancient stars, new ones arise, promising light, warmth, and future worlds. Deep within the heart of a collapsing protostar, something extraordinary begins to stir. As gravity pulls inward, the core grows hotter, and hotter still. Temperatures soar past millions of degrees. At this threshold, hydrogen atoms, the simplest elements in the universe, begin to collide with such force that they fuse. This is nuclear fusion, the moment when matter becomes light. Protons merge to form helium, and in the process they release vast amounts of energy. That energy pushes outward, fighting the collapse, creating a balance, a fragile equilibrium between gravity and light. This is the ignition, not of fire but of something far greater. A star is born, blazing at its core with the same force that powers the sun. It will shine for millions, even billions of years, converting mass into brilliance, becoming a beacon across space and time. From the cold silence of a molecular cloud to the furnace of nuclear fusion, the transformation is complete. The cosmos has lit another candle. After the explosive birth of a star, a long and stable chapter begins, the main sequence. This is not a moment but an era. A star will spend most of its life here, quietly and steadily turning hydrogen into helium in its core. Fusion continues, releasing energy that balances the inward pull of gravity with an outward push of light and heat. From the smallest red dwarfs to the giant blue stars, each follows this path. The exact size and mass of the star determine how bright it shines, and how fast it burns through its fuel. This phase is what astronomers call the main sequence, a defining feature in the Hertzsprung-Russell diagram, a cosmic chart where stars are mapped by their brightness and temperature. On this diagonal line, stars live out their prime, stable, radiant, predictable. Our own sun is in this phase now, and has been for billions of years. It is a stellar adulthood, where the star burns with grace and purpose. But even this long chapter is temporary. Eventually, the hydrogen runs low and change is inevitable. The star's quiet balance begins to tip, and a new transformation awaits. Nothing lasts forever, not even the steady brilliance of a star. After millions or even billions of years on the main sequence, a star begins to change. It has burned through much of the hydrogen in its core, the very fuel that kept it alive and stable. Now, gravity begins to win. With less hydrogen to fuse, the core contracts under its own weight. It grows smaller, hotter, and denser, a smoldering ember buried within. But as the core shrinks, the outer layers respond by expanding outward. Like a breath held too long, the star exhales. Its outer envelope swells, becoming vast and cool. The surface glows red, and the star becomes a red giant. This aging phase is both gentle and dramatic. The star is cooler on the outside, but more unstable within. In its final efforts to resist collapse, it may begin fusing helium or other elements in its deep core. Our own sun will enter this phase one day, swelling far beyond its current size, possibly engulfing Mercury, Venus, and maybe even Earth. What was once a quiet, balanced star is now enormous, luminous, and nearing the end of its life. But it still has one final act to perform. Some endings arrive quietly. Others shake the very fabric of the cosmos. The death of a star depends on how much mass it carried through life. And like with people, some stars fade away, while others go out with fire. Low-mass stars like our sun don't die in explosions. After the red giant phase, they shed their outer layers into space, creating a glowing shell, a planetary nebula. What's left behind is the hot, dense core, a white dwarf. It no longer fuses atoms. It simply glows, dimming, cooling, and waiting in silence for eternity. Massive stars, however, face a far more violent fate. Their cores collapse catastrophically, triggering a supernova, one of the most powerful explosions in the universe. For a brief moment, the star can outshine entire galaxies. It releases shockwaves, heavy elements, and radiation across light years, seeding the cosmos with the building blocks of new worlds. From this cataclysm, two outcomes emerge. If the remaining core is heavy but not extreme, it becomes a neutron star, a city-sized sphere of pure nuclear matter, spinning rapidly with gravity so intense it crushes atoms. Some shine as pulsars, emitting beams of radiation like cosmic lighthouses. But if the star was truly massive, even neutron matter cannot hold. Gravity overwhelms everything. Space itself folds inward. And so is born a black hole, an object with no surface, no light, no escape. What falls in is lost to time. The star is gone, but its death echoes forever. When a massive star reaches the end of its life, it does not go quietly. It erupts in a final act of cosmic defiance. A supernova, brighter than entire galaxies, brief and violent. In that blinding flash, the elements forged over millions of years, carbon, oxygen, silicon, iron, are hurled into space. This is not destruction. This is a beginning. The shockwaves from the explosion stir nearby clouds of gas, sowing the seeds for the next generation of stars. Dust and atoms from a single star may travel for millions of years, only to settle in a new system, a new world, a new form of life. Our own sun is too small to die this way. But everything around it, the iron in your blood, the calcium in your bones, the oxygen in your breath, was born in one of these titanic deaths. We are stardust. Not metaphorically. Literally. The atoms in your body were forged in the core of a long-dead star, scattered across space, reassembled by gravity and time, and shaped into something that can look back at the stars and wonder. And maybe that's the greatest legacy of all. Not just that we come from the stars, but that we know it. When a massive star dies, it does not simply vanish. It folds in on itself, collapsing under the weight of its own gravity. If its core is heavy enough, typically more than 3 times the mass of our sun, nothing can stop this collapse. The result is a black hole, a point in space where matter is so densely packed, not even light can escape its grasp. This boundary, the event horizon, marks the edge of no return. Anything that crosses it, light, matter, even time itself, can no longer communicate with the outside universe. And yet, black holes are not truly holes. They are extreme objects, warping space-time, spinning, and sometimes devouring surrounding stars and gas with violent hunger. They power quasars and shape galaxies. Though black holes are born in darkness, they do not live forever. According to physicist Stephen Hawking's prediction, they emit faint radiation, Hawking radiation, caused by quantum effects near the event horizon. This slow leak of energy means black holes may eventually evaporate over unimaginable spans of time, fading into silence. But until then, they remain one of the most enigmatic legacies of stellar death, a shadow cast by light, a reminder that even the brightest lives can end in mystery. The death of a star is not the end, it is a beginning. When a supernova erupts, it hurls its elemental riches across the cosmos: carbon, oxygen, iron, gold. These remnants drift through space, mingling with ancient dust and gas clouds. Over millions of years, gravity gathers these scattered fragments again, and a new star ignites. Around it, planets take shape from the same material, some eventually blooming with life. We are born from this cosmic cycle. The calcium in our bones, the iron in our blood, the carbon in every living cell, all were forged in stellar furnaces long before our sun was born. We are children of stars, both ancient and eternal. This unending rhythm of death and rebirth is the heart of the universe. In space, nothing is ever truly lost. Matter becomes memory, energy becomes motion, and even the silence of a dying star whispers the promise of creation. In the grand design of the cosmos, everything transforms. Everything continues.